Another definition related to the line of action is the arc of action. So the line of action was defined as the line along which the point of contact lies. So the teeth will not be always in contact. There will be a start point for contact and an end point. So there will be a finite portion on line of action for which the actual contact takes place. So during this finite portion, the wheels must have turned by some angular distance, so that the arc formed during this time instant when two teeth are in touch is called arc of action. So let's say this is a time instant when tooth, the tooth from the pinion first touched the tooth from the gear. So the gear position was like this at that time. This is the first point of contact, and this is the last point of contact. At this location, the gear wheel just left, the pinion wheel just left the, so it will be like this. The final point of contact is somewhere towards the bottom of the face. The initial point of contact is somewhere towards the top of the face. So this distance, let's say this point is A and this point is B, is the actual line of action where the point for contact takes place. So during this period, the pinion has rotated by some, the wheel has rotated by some finite arc. So if you draw a line to connect in the center on the line of action, you can draw an arc, okay, of the pitch circle diameter. Let's say the pitch circle diameter at the start and at the end. This will be the start of the pitch circle diameter. This will be some points that let's say a dash, the pitch circle cutting, and the pitch circle cutting this end point line, let's say B1. So this is A1 arc, A1 B1 is arc of action. Now arc of action is needed is to determine the contact ratio. So you know the arc of action and you know the circular pitch, that is the distance between two adjacent teeth, the pitch of the gear. So if the arc of action is having some distance and the circular pitch is a part of that, then at a time instant, if contact ratio CR is greater than 1, then arc of action will be greater than circular pitch. So that time more than one teeth will be in contact. So if you divide the arc of action by circular pitch, you will get the exact number of teeth. CR is exact number of teeth in contact at any given time instant. Why this thing is important? This thing is important to determine the load distribution on the gear teeth. So at any particular time instance, if T is the torque, then the force transmitted by the teeth is T by R, where R is the radius from the point of contact to the center of the gear wheel. So that force will be distributed across contact ratio number of teeth. If contact ratio is more than 1, the force will be distributed over more number of teeth, and you will get lesser load per teeth. So it is important in load distribution design. So because this will affect the stresses in the teeth and cracking and life of the teeth. Now we will derive the basic condition for gear formation, that is the condition for transmission of constant velocity ratio. This means that the motion transmission between the two wheels will be smooth and the angular velocity of the two wheels will be constant at any time instant. So if the pinion is rotating at an angular velocity of omega, let's see omega, and the wheel is rotating at an angular velocity of omega and will be constant on the time over at all instances in time. For achieving that, this sounds like a simple task, but for achieving that, a special kind of gear profile is needed. So we will do a derivation with that. Any general gear profile will not do that. It will do the motion transmission with jerks. For a smooth transmission with constant velocity, a partial condition has to be satisfied. That will derive now. For doing that, we will draw a line which is a common tangent to both of the pitch circle, and it will obviously pass through the pitch point. Let's say this is a line, and then we have a line along with the normal force X. This is called normal force or pressure line. So when the two teeth are in contact with each other, there will be a surface, and the normal force will be transmitted. So let's say that they are in contact at point C, and the profile we don't know yet. We are doing the derivation for the profile only. So the profile is such that this is a line passing through along the line of the normal force, and this is the common tangent. Common tangent to pitch circle PC. So let's say these two lines are at an angle of xi. Now the velocity of the point of contact will be same for both the gears. So let's say this C is a point of contact. So the velocity of point of contact on the pinion will be tangent to the line connecting O1C. So let's say this is a line. So this is a velocity vector of the point C from the point of view of pinion, the O1C circle. So it is perpendicular to O1C, the velocity of point C1, VC1. So C1 is the point C on pinion, which is having center O1, and C2 is point C. Both points are same, they are in contact. So point C on wheel, which is O2. So let's say VC1, and let's say VC1 makes an angle alpha with respect to the normal force line, the pressure line. And similarly, there will be a velocity for point C, VC2. It will be perpendicular to the line O to C. So this is line VC2, the velocity of point C2, and this will be perpendicular to the O to C. And let's say this makes an angle beta. So this angle is beta with respect to the normal force line. So I'll just draw it here, write it here. VC1 is perpendicular to OC, and VC2 is perpendicular to O2C, and VC1 is at alpha degrees to normal force line, and VC2 is at beta degree to normal force line. Now we will draw some more construction on this diagram that will help us in derivation. So we will drop a perpendicular from point O1 to the normal force line, let's say here, and this point we will call as I1, which is perpendicular to the normal force line. Similarly, we will drop a perpendicular from O2 on the normal force line, and let's say this point. Now if you see the angle O1 P I1, and since VC1 is perpendicular to line O1P, so the angle between this line P1 is along the force line. This is alpha that we assume, So this, if this is alpha and this is 90 degree, O1 P VC1 is 90 degree. So this angle O1 P I1 will be 90 minus alpha. And since this is a right angle triangle, this angle will be alpha. It is pretty much straightforward from the elementary geometry. This will be alpha. Similarly, in this triangle, this O2, I2 and C. In this triangle, O2, O2, I2, C. In this triangle also, since the angle O2C VC2, like I2C VC2 is beta. This is I2, this is C, this is VC2, this is beta. So this angle is 90 degree. So here this angle will be 90 minus beta. C I2 O2 will be 90 minus beta. So this angle will be equal to beta. So alpha is the angle of VC1, the velocity of point C1 with respect to the force line, and that's by the geometrical consideration we saw that this is 90 minus alpha, so this is again alpha. Similarly here we saw that this is beta. Now from the condition of transmission of constant velocity ratio, we know that VC1 cos alpha is equal to VC2 cos beta. That means the component of VC1, this is the velocity VC1, the component of this velocity along the normal force line. So this is a normal force line. So along this line, the component of VC1 will be equal to the component of VC2 along this line. The component of VC1 along normal force line will be VC1 cos alpha, and VC2 will be VC2 cos beta, because it makes the angle beta degree. So if you further simplify this expression, VC1, we know that velocity is equal to angular velocity into the distance, the radial distance. So O1C, V1 is equal to omega into O1C1. Similarly, VC2 will be ohm into O2C2. So we'll substitute these values here. Omega O1 C1 cos alpha is equal to ohm O2 C2 cos beta. Now these quantities O1 C1 cos alpha and cos beta we'll see from the geometry. O1 C1 and I1 is one triangle. O1 I1 C1. So in this triangle, O1 C1 cos alpha will be equal to O1 I1, this length. And similarly here, O2 C2, C is the same point, C1 C2 is the same point C. Cos beta will be equal to O2 I2. So hence you can replace here omega into O1 I1 is equal to ohm into O2 I2. Remember that I2 is a point where the normal from the center is drawn on the normal force line. So that point becomes I2. And similarly I1 here. So from the similarity of the triangle, we see that from similarity of triangle O1 P I1 and triangle O2 P I2. Remember that this time we have changed the triangle. We are not talking further about the triangle O2 C I2 or O1 C I1. We are now talking about the point P, the pitch point. So O1 P I1 and O2 P I2 are similar. That's why O1 by I1, O1 I1 by O2 I2 is equal to O1 P by O2 P. So hence omega by ohm is equal to O2 I2 by O1 I1. This is equal to O2 P divided by O1 P from similarity of the two triangles. Now if omega by ohm ratio is to be constant, then P must be a fixed point. This is very simple to understand, common logic. That the P cannot keep changing with time. the pitch point has to be constant. The pitch point lies on a line connecting the two centers. The pitch point should divide the two lines. Pitch point P1 must be constant in space and must divide the center line connecting the two centers in velocity ratio. So this is the condition for transmission of motion through gears. So while starting the derivation, we didn't make any particular assumption on the normal force line. We assumed the normal force line for any general profile. So it was not necessary that the normal force line will pass through the point P. If you change the angle, the profile is changed, it can pass to some other point. While the P is a constant point which divides the line connecting the center in the velocity ratio. So the point P is fixed for the gear, but the profile can be anything, the angle can be anything. So from this derivation we saw that for constant velocity ratio transmission, the common normal at the point of contact must pass through the pitch point. So this is now the common normal at the point of contact, that is the force line direction, is fixed now. So it has to, and there can be any general point C for contact, but the general normal at the profile should be such that it should pass through, the normal to the profile should pass through P. This condition is fulfilled by the teeth of involute form. So involute form, you have a circle, there is a tangent, and the profile is such that when you open the spool of thread, this profile will be drawn. So any point of this on the profile will have a tangent to the circle. So now we will show you the real strength of the involute profile why it is used in the gears. So if you draw perpendicular from the involute profile, there will be a base circle. So this is called the base circle, which is generator of involute profile. Involute profile. So any normal, and at normal at any point on the involute profile is tangent to the base circle. Because I told you earlier that involute profile is formed by opening a thread from the spool. So the thread will be a straight line always, and it will be tangent to the surface formed by opening the spool. So normal, if you take the involute profile, this is the profile used for gears, involute profile. Normal at any point will be tangent to the base circle. So this gives us now the definition of our base circle. So this is the gear profile. Point C is the point on the gear profile, and normal to that is passing through the pitch point, and it will be tangent through a base circle. So the base circle will be formed by line I2, O2. Similarly here I1, O1. So this will be forming the base circle. So since the condition of tangency has to be satisfied, if you take C at any point, the line of force will be tangent to the point I2. So this circle will be constant. Since your force line is in a constant direction, the direction of PC is constant. Direction of PC is constant. So hence the triangles OPI1, O1PI1 and O2PI2 constant for any gear configuration. If the condition for constant velocity ratio has to be satisfied, then it is simple, straightforward that P must be a constant point, and the triangle O C O1 I1 P and O2, I2, P are constant. So since these two triangles are constant, then the base circle will be also constant at any time instant for the gear. It will not depend on the point of contact C. The C will be traveling along the force line, the line of action, but the base circle will be constant. So after this derivation, we also understand that the line of action is same as pressure line or the line of contact. So all these three are same, and it is also constant for the given gear configuration. So we can do the derivation for that. For all this derivation, the interesting thing is to know that we need to know only velocity ratio. So from velocity ratio, we can divide the line connecting the centers of two O1, O2 at point P, which is a pitch point. This will divide the O1, O2 into a velocity ratio, and from pitch point, we can draw a line along the point of action. You can draw the base circle and draw the involute profile. You can get almost all the quantities. This diagram will again allow us to do one more derivation, that is a derivation for velocity of sliding. So I told you earlier that in the gear the motion is mainly rotational. So the involute profiles are sitting on top of each other, and when they are moving, there is purely a rolling contact, since the angle alpha and beta are usually small, but still there will be a slight sliding velocity. Because of that, the friction will come. So how to go on about determining the velocity of sliding? So from this figure earlier we saw that Vc1 cos alpha is equal to Vc2 cos beta. From this condition we derived the condition for involute profile of gear, that P must be a constant point of this circle, and the normal from the gear profile should pass through P. We derived that. Now we will use the same velocity triangle. So the velocity of sliding, now we will look along the gear profile. So we will see the velocity component of the points on gears along the gear profile. So velocity of profile will be Vc1 sine alpha minus Vc2 sine beta. So the Vc1 sine alpha is the component of velocity along the gear profile. So this is Vc1 sine alpha, and similarly Vc2 sine beta along the gear profile. Difference of these two will be the velocity of sliding. We know the Vc1 is equal to omega OC1 O1 C1 sine alpha minus ohm O2 C2 sine beta. From this triangle we see O2 I2 sine beta is equal to I2C, and from this triangle OC1 I1 we see it is equal to I1C. So we will substitute these values here, equal to omega I1C minus ohm I2C. Now I1C is equal to I1P plus PC, and I2C is equal to I2P minus PC. This we are doing to have a because the point P is fixed point. So express the point C. Here the quantities are in terms of C. We are expressing them in terms of P. So omega I1P plus PC minus ohm I2P minus PC. This we have seen through the geometry. Now omega I1P minus ohm I2P plus omega plus ohm into PC. Now again from the velocity triangle, ohm into I1P, this is equal to omega into O1P, because the point P is constant. So these two quantities are equal. Ohm into I1P is equal to omega into I2P, so this will be equal to 0 from the condition of transmission. So hence we are left with velocity of sliding is equal to omega plus ohm into PC. What is the distance PC? PC is here the distance between the point of contact and the pitch point. Now from this expression you can see that the maximum velocity of sliding will occur at maximum velocity of PC. So when C is close to P, the velocity of sliding is very less, and when C is far away from P, the velocity of sliding is maximum. So velocity of sliding is maximum at first or last point of contact and 0 at pitch point, because the point of contact and pitch point will be 0. So due to that we will try to minimize the path, the travel of the teeth in contact. For that we have to increase the number of gears, increase the number of teeth to have a smaller path of contact, and hence we'll have less sliding, less friction and lossless transmission, which is the chief advantage of the gear. So since the path of contact is important for getting the sliding, we will do a derivation for the path of contact. For that again we will use the same diagram, but this time we will take the addendum circles also in consideration. The idea is simple. You know the gear profile and you know the line of action and you know the addendum circle. So you find out the point where the addendum circle cuts the pressure line, the line of action. So, addendum circle. You draw the 3 stages of engagement, that is first contact. First one is the first contact, assuming that omega is in this direction counterclockwise and ohm is in in clockwise direction. Then the first contact will occur something like this. This is the teeth on the pinion, this is the teeth on the gear, and somewhere here at the addendum only it will happen, first contact. And this there will be line of action, it will pass to the point P, the P circle point. Then at the center, when both the teeth are at center, they will touch somewhere at the center of their profiles. So this is the teeth on the wheel, and this is the teeth on the gear, on the pinion, and they touch somewhere in the center. So this is center. And the last point, when they are leaving each other, this is the teeth on the pinion, this is the teeth on the wheel, and here the addendum circle of pinion will come in place. In first one, the addendum circle of wheel was in consideration. In this one, the addendum circle of pinion will be important. So this will be the last point of contact. Let's say the first point of contact is A, the last point of contact is P, B, and the center one is obviously the P, the pitch point. So in this diagram, let's say A occurs somewhere here. We don't know the exact position yet. It will depend on the addendum circle diameter. This is A, and the B occurs somewhere here, the last point of contact. And we are interested in finding the distance AB. So first we will divide it into 2 parts. First we will calculate AP between the P circle point and the first point of contact, and PB, and then from the geometry of this diagram we will determine the distance AP. So AP is equal to AI2 minus PI2. Now we know the distance PI2. PI2 is nothing from this triangle O2PI2, which is a constant triangle for a given gear configuration. So O2P is R, the radius of pitch circle, and this is small r, the radius of pinion pitch circle. Let's say RA is radius for addendum circle of wheel, and small ra for pinion. So from this geometry, this distance pi2 is equal to r sine xi. So this angle xi is constant because the triangles are constant, pitch point is a constant. So this, if this angle is xi between the common tangent between the pitch circle line and the line of action, if xi is the angle, and since p, this angle is perpendicular to the common tangent and line connecting the center, so this angle O2pi2 is angle O2pi2 is 90 minus xi, and angle I2 O2p is xi. So, and this was equal to beta, that was for a common, it's any general point of contact. Now we are talking about point P, the pitch point. So xi will be constant, the distance between the common tangent to the pitch circle and the force lines, the angle between them. Similarly, here in this diagram, this angle which is connecting the pitch line up to the pitch line, center line, will be equal to xi. So hence the distance pi2 will be r sine xi from the right angle triangle. Triangle O2 I2P, distance pi2 is r sine xi, and here the other distance we are interested is a I2. So if you form a triangle connecting O2 and A, then from we know the O2A. O2A is nothing but 2A is RA, radius of addendum circle of wheel, and this distance O2B, you know, O2B is R cos xi. O2B is R cos xi. So from right angle triangle, O2A I2, the distance A I2 is equal to RA square, that is a hypotenuse, and the base. The base is R cos xi square. Hypotenuse minus cos square root will be perpendicular. So in this right angle, O2A I2, we are creating another triangle.